Dear classmates, welcome back to the DFT JTAG chapter. In our previous video, we have introduced JTAG components such as test access port and the tab controller. In this video, we are going to introduce JTAG register and the instruction decoder. There are two types of JTAG registers: data register or DR and instruction register or IR. There are two important data registers: bypass register or BR and the boundary scan register BSR. These three types of registers are mandatory registers. It is required by the JTAG standard. There are some optional data registers such as device ID register and device-specific registers. They can be decided by the designer. In this lecture, we are not going to cover the optional data register. From this figure, we can see that this register shares the same test data input pin, TDI. We broadcast the test data to all the registers. And then the scan output of this register are marked and shared by the same test data output pin, TDO. So first, let's introduce the bypass register, BR. The purpose of bypass register is to provide a shortcut from TDI to TDO. The structure of a bypass register is very simple. It is just a 1-bit flip-flop. When the control signal shift DR is equal to 1, we can shift our test data from TDI to TDO. In this way, we provide a shortcut through this chip. So this chip is not tested by JTAG. Here is an example. Suppose on this board we have three chips. Chip number 2 and the chip number 3, they are tested. So they are called chip under test. However, chip number 1 is not tested by the JTAG. If we want to go through all the 24 boundary scan cells, we would need 24 clocks. However, if we use the bypass register of chip number 1, we can simply use 1 cycle plus 8 plus 8, which is 17 clock cycles. In this way, we can reduce 29% of our test time. So, bypass register help us to save test time. Now, let's move on to the most important register, the boundary scan register, BSR. The boundary scan register, BSR, control our system input pin or output pin. We can also observe the system input pin or output pin. As is shown in this figure, the primary input of this chip is called system input pin, and the primary output of this chip is called system output pins. In JTAG, we stitch the system input pin and the system output pin into boundary scan register, and the boundary scan register consists of input boundary scan cell on our left hand side and output boundary scan cell on our right hand side. So in JTAG, we can shift in our test data through the boundary scan register and shift out our test response through the boundary scan register. So the boundary scan register is one of the most important components in JTAG, and it forms boundary scan chain so that we can apply and observe test data. Now let's look into the detailed structure of input boundary scan cell (BSC). In the figure on the upper right, we can zoom in this square, which is the input boundary scan cell. On our left hand side is our system input pin. On our right hand side is the system logic. In this input boundary scan cell, we have two flip-flops. They are capture/scan flip-flop and output flip-flop. We have two control signals, shift DR and the mode. We have two clocks, clock DR and update DR. Totally, we can support 4 different operations using an input boundary scan cell. The first operation is normal operation. In this operation, the control signal mode is tied to logic 0, so that the input signal is coming in directly from the system input to the system logic, and the boundary scan cell is in a transparent mode. On our upper right figure, we can see this operation. The input signal just coming in through the input boundary scan cell. In normal operation, we clock the system clock to operate the system logic. The second operation is scan operation. In this operation, the control signal shift DR is tied to 1. So the test data is shifting from the last scan cell through the first flip-flop to the next boundary scan cell. So this is why we call it the scan flip-flop. In the scan operation, we use the clock DR to shift the boundary scan cell. Please note that the JTAG boundary scan cell has 2 flip-flops. So in scan operation, the system logic is totally isolated from the scan chain shifting. So boundary scan does not interfere with system logic. Operation number 3 is the update operation. In this operation, when we pause the update DR clock, the test data is transferred from the scan flip-flop to the output flip-flop. So in this way, we can apply our test pattern to our system logic as is shown in the upper right figure. And the last operation is the capture operation. In this operation, we pause the clock DR and the control signal shift DR is tied to logic 0. In this way, we can capture the value from the system input pin into the first flip-flop. This is why we call it the capture flip-flop. As we can see from the upper right small figure, the capture operation captured the logic value into the boundary scan cell. Now, this is the summary of the 4 boundary scan cell operations. In normal operation, the system pin is connected directly to the system logic, and the boundary scan cell is transparent. In scan operation, the boundary scan cell is shifted from one cell to another cell so we can load the test pattern. In the update operation, we can update the output flip-flop and apply our test pattern to the system logic. And finally, in the capture operation, we can capture the test response into our boundary scan cell. So when we are running the boundary scan testing, we can load our test pattern using the scan operation, and we can apply our test pattern using the update operation, and we can capture test response using the capture operation. So these 3 operations are repeated and repeated again and again to apply test pattern and observe test responses. Now, let's look at the other side, the output boundary scan cell. On the upper left figure, we zoom in this square. We can see that the output boundary scan cell is actually very similar to the input boundary scan cell in the structure. It also has 2 flip-flops, 2 mugs, 2 control signals, and 2 clocks. The only difference is that now the system logic is on our left and the system output pin is on our right. So the direction is the opposite to the input boundary scan cell. Now it's time for you to work on the quiz. Given the output boundary scan cell, now please fill in this table for the clock column to accomplish the 4 operations. Okay, are you done yet? The answer is actually the same as input boundary scan cell. In normal operation, we clock the system clock in system logic. For scan and the capture operation, we pause the clock DR, and for update operation, we clock the update DR. Have you got it correctly? Now let's move on to the second important register, the instruction register. The purpose of instruction register is to shift in our instruction from the TDI input. It also stores JTAG instruction for instruction decoder. This slide shows the architecture of instruction register. It is very similar to the boundary scan register, which has 2 layers of flip-flop. The scan flip-flop and the second layer is the output flip-flop. So how do we load the instruction? First, we hold the control signal Shift IR to 1. and we pause the clock IR. After we have loaded the instruction, then we pause another clock update IR so that we update the instruction into the output flip-flop, which is then sent to the instruction decoder to generate control signals. We have these two layers of flip-flop design because during the scan operation, we want to isolate the instruction decoder from the scan operation. So how do we load an instruction? From this JTAG tap controller's finite state machine diagram, we can see how to load the instruction. First, we want to initialize the JTAG test logic. We can apply a sequence of 5 ones to TMS. This tap controller can be initialized in this way, regardless of the initial state. This is a very smart design to reset the JTAG logic without an extra pin. So, no matter where we are initially in this finite state machine, we are guaranteed to be reset to the test logic reset state. You are welcome to check if this is correct or not. Now, starting from this test logic reset state, we can apply a TMS sequence of 0, 1, 1, 0, and 0, which will bring us to the shift IR state. In this state, we can now load the instruction. When we load the instruction, TMS is 0 all the time, so we can keep in the shift IR state, and our instruction code can be shifted in via the TDI input. When we are done, we can now leave the shift IR state by applying a TMS sequence of 1, 1, 0. This will bring us back to the run test idle state. And then we are finished loading the instruction. Finally, let's talk about the instruction decoder. This slide shows a nice summary of the JTAG components we have introduced so far. On the tab, in this dashed rectangle, it is data register. We have boundary scan register, bypass registers, and the other optional registers. In the middle of this figure, we see instruction register and the instruction decoder highlighted. The instruction decoder generates control signals such as mode to the data register. It also generates the select signal, which controls the scan output for the data register. On the lower left, we see tap controller, which is a 16-state finite state machine. The tap controller generates clock DR, shift DR, update DR to data register. It also generates clock IR, shift IR, update IR for instruction register. Please note that the clock DR and the clock IR are active at the rising edge of the test clock TCK. Also, the tap controller make a state transition at the rising edge of TCK. On the contrary, the update DR and update IR are active at the falling edge of TCK. Also notice that the TDO output is available after the falling edge of TCK. This is specified by the JTAG standard. In summary, in this video we introduce the data register, which consists of bypass register and boundary scan register. In each boundary scan cell, we have two control signals shift-DR mode. We have two clocks. We can support 4 operations: normal operation, scan, capture, and update. We also introduce the instruction register, which store the instruction and provide the instruction to the instruction decoder to generate control signals. Thank you for watching.